So this is chapter 21, problem 14. And here we're told that we have part of a single rectangular loop of wire with dimensions shown in the figure, and situated inside of a region of uniform magnetic field with a particular strength. Total resistance of the loop of wire has some number of ohms of resistance, and we're supposed to calculate the force required to pull the loop from the field. So we're supposed to we're trying to pull the loop and pull it at a constant velocity of 3.10 meters per second, neglecting gravity, of course. So you might wonder, why is it that one has to even apply a force to move an object at a constant speed, and if you do at all, how much force do you have to apply? And so it may be useful to go back and think about what is happening here. There will be a magnetic force on this wire if there is current in it. So remember that the magnetic force on a wire involves the current in the wire and its particular length and the magnetic field strength. And of course there is also a sign of theta here, but the orientations are always such that the theta is equal to 90 degrees, so we'll get to neglect that term. However, the current is oriented in this wire. If you think about it, suppose that the current is going up. I'm not sure which way at the moment, which way it goes, but whichever way the current may be going, if there is current going, suppose it goes like this, then you could use your right-hand rule to figure out what the direction of force would be over here. But whatever the direction of force is on this wire, it's going to be equal and opposite to the force on this part of the wire, and so those will cancel. And so all we really need to do is focus on the force acting on this piece of wire over here. I'm now going to get rid of these arrows, and we should think about why in fact there may be current going through this wire at all. Well, remember what's going on here. You have a loop of wire. There's some area, there's some magnetic field, there's some magnetic flux, and as you pull on the coil, of course you're going to change the flux through this coil, and Faraday's law of induction will tell us what the EMF, the induced EMF, is in that loop of wire. Other things we need to write down then, of course, is how can current be induced? Well, there is a formula to tell us what the EMF is. It involves minus the change in the magnetic flux divided by the change in time. And lastly, I'm going to write this a second equation in line here. Whatever that induced EMF is, that should be related to the current through the coil times the resistance R, and that's just Ohm's law. So really there are three equations we might want to think about here. Okay, so let's see. Let's go ahead and do this. So thinking about the force that is pulling, that we presume if we have to apply a force, it must be that this force, magnetic force on the wire, is going like this, and we are applying an equal and opposite force going the other way, resulting in a constant velocity. So the fact that the constant velocity must indicate that the force that we are applying, I'll call this F applied, is equal in magnitude to the magnetic force. The magnetic force is given by ILB. And I, the current in this coil, must be related to the EMF divided by R. So I'm going to go ahead and write this in two steps. I'm going to remind you that the current is EMF divided by R. Here's an L and here's a B. And the EMF is something that we may have discussed in class, but I think we should go back and talk about where it comes from. So we'll come back to this in a moment. How do we actually figure out what the EMF is? The EMF involves the change in flux divided by the change in time with a minus sign there. So I'm going to write it like this: minus, and then whatever the final flux is, subtract the initial flux. These are magnetic flux is what we're talking about, and divide by the change in time. There's a formula for what the magnetic flux is. Let me go ahead and put that down here as well. Magnetic flux involves magnetic field strength, the area over which that magnetic field is acting, and then of course there is a cosine of theta. I'll call it theta here. Remember, this is the angle between the magnetic field strength and the area vector, which is always pointing normal to the area itself. But in any case, what we have here is a magnetic field either going in or out of the page, depending on whether you're watching this video or recording it, and the area vector, that this angle is always going to be 0 degrees, so that's not a problem there. What is changing, of course, though, is not the magnetic field strength, but the relevant area. So if you like, as you look at this picture, the area you would use to calculate the flux through this loop is not the entire area of the loop, but rather just the area over which there is non-zero magnetic field. What that means is when we go to compute this, there's a minus. The final flux involves that magnetic field strength, but then, if you like, the final area. And what's initial, what's final? Well, all we have to do is think about any change in time. It could be here, and we move it over a centimeter or 2 centimeters or whatever. Whatever the change in the area is what we will need to stick in. Initially, we've got the magnetic field strength and the initial area. And of course, this is divided by the change in time. So we may have gone over this in class, but it's probably worth reiterating what's going on. If this is the initial position of the wire, when we shift it over a little bit, it's now going to look like, let's do this dashed line here. So if you like, the amount that the relevant area has changed, you can say, the change in the area really involves this delta x. That's this width, and then the length is here, L. And so let's stick that in here. When we go to compute, when we factor out B, which appears in both terms, minus B, and a final area minus an initial area, remember, this is the change in the relevant area over which there is non-zero magnetic field. That change in area is simply delta x, which is the distance that the coil has moved, times the length of the coil in this direction. So that looks like minus B times a delta x times an L divided by delta t. And this is where we finally notice, oh, it doesn't matter over what distance and what time we were asking. What you see, what shows up here, is delta x divided by delta t. That, of course, is the speed, or I guess technically it's velocity, the way we've computed this. So this is a long story short, this is a minus BVL. As you'd expect, the induced EMF should depend on the speed with which you're pulling the coil. If you don't pull it at all, and so the speed is 0, there is no induced EMF. That being said, we now have rederived our expression for the induced EMF on a coil being pulled through a magnetic field, and we're ready to get our final answer. Apparently what this means is that the force required to pull the coil at constant velocity equal to the magnetic force acting on this coil involves EMF, which we've just computed, and there may be a sign error here, I'm not sure, but let's call this minus, and put in the BVL, divide by the resistance, and we'll multiply this by L and times B. When we clean this up, you'll see there's 2 factors of B, 2 factors of L, and there's a minus sign, which I've left around. There's a B squared and an L squared and a V over R. And perhaps what we can do is at least just worry about what the absolute value of this applied force is. I suspect that this minus sign is probably just an indication of Newton's third law, but let's just worry about the magnitude. This is B squared L squared V over R. In this problem, we were given B. Let's write down that number. They give us B is 0.550 Tesla. The resistance is 0.23 ohms. The speed was 3.10 meters per second. The length is 0.350 meters. You notice they also give you the width in the problem, but it's not a number that you actually need. So we have B, R, V, and L, and that's everything that we need. When you plug everything in, what you should find is that this is actually 0.499 newtons, and if you should, in fact, keep this to 3 sig figs, because everything here is given to 3 sig figs. So that is the applied force, and that's the answer you get. Now, what I'm going to do is also just quickly tell you that there's another way to view this problem. You can think about this instead in terms of energy and power. So think about this. You're applying a force to this coil. You're applying this force and you're displacing the coil, which means that you're doing work. And you're displacing that coil at a certain rate, at a certain velocity, which means that you're doing work at a certain rate, or in other words, you're applying power. If you think about it, the power that you provide, power, P, is given by the amount of work that you do divided by the time that it takes. In other words, the force you apply times the displacement divided by delta T, which of course is just the force times the speed with which you are moving it. Now that power that you provide to the coil, the only way it can be consumed in this ideal setup is through the electrical dispersion of that energy into the resistance in the wire. Okay, so it's therefore useful to think back to what is the power consumed by a wire with current in it and some resistance. You can write this as I delta V, or you can write this as I squared R, or you can write this as delta V squared over R. So all three of those are the same. But the whole point is you're going to now equate this. You're going to equate the power that you provide to this setup to the power consumed by the setup. When I write delta V, what I really mean there is the EMF. In other words, you can set the EMF squared over R, that's what I'm using this expression here, you can set that equal to the force that you provide times V, and so you can then solve for the force that way. So apparently the force is equal to EMF squared over R over V. Getting the EMF is something that we already did. The EMF is, the magnitude anyway, is BVL, and you square that, and so this should be BVL squared. There's a minus sign, but that goes away, and divide by R and V. In the end, what you notice is you get a B squared, you get an L squared, and a V over R, just like the answer that we got the other way. So in any case, there are at least two different ways to look at this problem, but in the end you get the same answer. So that should be your result, and there you go.